Okay, let us begin. So, yesterday we started talking about propositional logic. So, propositional logic is also known as the logic of connectives, and we saw using just two connectives, one is unary connective, namely negation, and the second one is binary connective, namely conjunction. Using these two connectives, we constructed all sentences for a given propositional language. And after that, we also stated the unique readability theorem. So, the purpose of unique readability is, of course, as the name suggests, unique readability, which means that one particular formula cannot have two different forms. It cannot be negation of something as well as conjunction of something, or it can be a propositional variable. A propositional variable itself is not negation of anything. It's not conjunction of two smaller things, right? Or a negation cannot be a conjunction. Even a conjunction S1 conjunction T1 cannot be equal to S2 conjunction T2 unless and until S1 is equal to S2 and T1 is equal to T2. So, for computers, or for any formal system, it makes life easy. And for mathematicians, it makes life easy by its utility in proofs, because whenever we want to prove something, we will only prove it for one particular form, and that is precisely what we are going to do now. We are going to look at one application of the unique readability theorem, and this is what we are going to start with. Okay. So, yesterday we also defined a valuation or a model. Valuation or a model is a function from the set of L formulas to truth and false. So, we assign a truth value to each formula in such a way that negation always gets the other truth value and conjunction gets truth value true if and only if both the statements are true. Any questions about this? Okay, now tell me, is L a subset of SL? Yesterday we used some notation. What is L inside SL? S0L, right? So, S0L. So, in particular, if I have a valuation, then I also have a valuation of the propositional variables, right? So, given a valuation V from SL to true and false, we also have a function V0 from L to true false. Okay. So, see, this is the first one is a valuation. The second one is merely any function. I mean, a valuation is a function which satisfies some properties. But when we are restricting a valuation only to the language, we don't need to satisfy any properties. It's plain and simple. It's any function. Obtained as the restriction of V, this is V, to L equal to S0L subset of SL. Correct? Okay. However, conversely also, now this is a proposition, not as in propositional logic, just a proposition to prove, it's a statement to prove, proposition that given any V0 from L to T truth and false, there is a unique valuation V from SL to true and false, satisfying V of P equal to V naught of P for all P in L. So see, what does this statement say? That every valuation restricts to a function on the language. Now here we are saying that every function extends to a unique valuation on the set of L formulas. Is this surprising? See, if I have variables P and Q, and then I want to assign truth value to P conjunction Q, and I know the values assigned to P and Q, truth values of P and Q, then can I assign the value to P conjunction Q? Can I assign value to negation Q? So everything is automatic, right? I mean, checking this is very hard. As soon as L contains at least one element, SL contains infinitely many elements. So we are not going to check for all formulas whether this is true or not. The simpler thing is just start with the language and define any function on the language. This is what we mean by a row in the truth table, correct? If I say P is true, Q is false, then I can evaluate the truth value of any formula which contains only P and Q, right? So that's what we are going to prove. And how should the proof go? If we want to define something, what should we do? What is the only way of defining functions? Recursion, very good. So define V recursively as follows. The first one, so base case, we just have to take care of this particular property. What is the property? Vp is equal to V0p. So base case will define Vp equal to V0p for any P in L. That's where we had to start. Now the inductive case, I mean maybe I should write as 0L. So inductive case or recursive case. So now given any formula which is not in S0L, what do we know about it? It belongs to some SNL. Yeah. So given any S in SNL, but I mean it belongs to a unique SNL, correct? So I can also say something more. It belongs to this but not in SNL. For n belongs to omega. Now here there is a formula which is in Sn plus 1L, so it has n plus 1 parenthesis, but it doesn't have just n parenthesis. However, by unique readability now, we know that it is exactly one of the two forms. And those two formulas, if it is negation, then what is it negation of? That is uniquely determined. If it is conjunction, then what is it conjunction of? That is uniquely determined. That is the purpose of unique readability. By unique readability, exactly one of the following is true. Okay, the first one is that S is equal to negation T for some T in SNL. Yeah, this T has to come from the lower portion. And SNL is actually union of S0, S1, S2 up to Sn, everything cumulative. Okay, so S is equal to negation T for, so in this case, define V of S. Now we want to define V of S. How should we define it? So S should be true if and only if T is false. And see, by induction, the value of T is already known. So this value, so this known by inductive hypothesis. Huh? Sorry, yes, false. Okay, and secondly, what can it be? S is equal to T conjunction U for some T and U in SNL, and in this case define V of S is equal to true. Whenever I say define, then I use colon equal to, yeah, definition equal, if and only if V of T is true and V of U is also true. And that's how you define a function. It clearly agrees with V0 on L, and that's the end of the proof. So basically, a valuation, even though it looks complicated, we don't really have to check it for infinitely many formulas. It's enough to start with any random function from L to truth and false. So you simply assign truth values to the propositional variables and every other truth value is determined. Any questions? So that's precisely what we do, yeah, in the case of truth tables. Okay, now some nomenclature time. So given a propositional formula S implies T, yeah, what is its converse?
T implies S.
What is its inverse?
S complement implies T complement.
S?
S complement implies T complement.
S complement implies T complement. That's not the correct language. Negation S, negation T. Okay, what is the contrapositive?
Negation T implies T.
Now, whenever we try to prove a theorem, yeah, then there are two options, either proceed directly or prove its contrapositive. Yeah, we did the contrapositive proof for Stone's representation theorem, order reflecting part, right. So, these are four statements. So basically what we are trying to say that S implies T is the same as negation T implies negation S. But are they syntactically same? Syntactically as in do they look exactly the same? Do they read the same? No. But they are same. So what does it mean to be same? Same? Same semantics. Okay, semantics is a valuation for us. So what does that mean? They have the same truth tables, yes. So let us write that thing down. So let us write a formula. I'm only going to do, well, yeah, I mean, you are not children anymore. I need to draw the truth tables for these 4 formulas? Yeah, you know what they are. Let me directly start with the definition. So say that S and T in SL are logically equivalent if for any valuation V from SL to true false, we have V of S is equal to V of T. So this notion really captures what we want to say, that their valuations, their truth values are always going to be the same. Yeah, so truth value of S implies T will always be truth value of negation T implies negation S for any given valuation. So some standard logical equivalences. Okay, I am going to list a few, you can complete the list later. First one, what about S conjunction S? What is it in logically equivalent to? And S is logically equivalent to? Then this is also logically equivalent to double negation of S. Yes, all of you know this? You can prove this? Good. Second, well, our parenthesis played very important role until now. But when we are just talking about one binary operation, then we don't really need to care about parenthesis. But of course, S conjunction T conjunction U and S conjunction T conjunction U, these are not equal because they differ in parenthesis. These are not syntactically equal, but they are logically equivalent. Correct? Okay. Then if you have two different operations like this, what will it be logically equivalent to? S, say it loudly, everybody. S conjunction, disjunction, S conjunction U. Okay. Yeah, practice saying it loud because you might confuse between meets joins and this. Okay, so this is again a logical equivalence. So other distributivity law should also hold. Then of course, once we are talking about distributivity, we should also talk about commutativity. So S conjunction T is same as T conjunction U. Sorry, T conjunction S. Up to logical equivalence, yeah, not otherwise. And perhaps you can list a few more, right? So these are logically equivalent statements. Okay, now so you can observe one thing, that whatever we are writing, whatever are the desirable properties of our connectives, they are not syntactic properties, but they are going to be semantically equivalent. Yeah, associativity up to semantic equivalence, up to logical equivalence, commutativity up to logical equivalence, then idempotency of conjunction up to logical equivalence. What does that tell you? That if we take the logical equivalence classes of these propositional formulas, then what would they be? What would they form? the logical equivalence classes of these formulas, they form a Boolean algebra, right? So, before I go there, maybe I will add one more. So, if I take S conjunction negation S, what is it logically equivalent to? It's always false, right? So, it is also logically equivalent to this, and similarly S join negation S is logically equivalent to T join negation T. See, if S and T contain different propositional variables, then also it doesn't matter. Logical equivalence is not a functional notion, as in it doesn't depend on the values, it doesn't necessarily depend on the values of the truth values of the variables inside it. These two examples 5 and 6 show that. Okay. So, I am going to write a definition. Say that S in SL is a tautology if V of S is equal to true for any valuation V. Tautology is some statement which is always true. In our culture, Raja Harishchandra, somebody who always tells truth, right? So, and a contradiction is a pathological liar. Yeah, contradiction. If V of S is equal to false for any valuation. So, what is a tautology? Well, S disjunction negation S is a tautology. S conjunction negation S is a contradiction. Now, what is the role of tautologies and contradictions? If I give you two different tautologies, then what can you say about their logical equivalence? They are logically equivalent, right? So, the logical equivalence class of a tautology will be what in the Boolean algebra? 1. And the logical equivalence class of contradictions is the 0. Okay. So, then, okay, let me directly start with the definition. For a propositional language L, its Lindenbaum-Tarski algebra BL is the set of logical equivalence classes of L formulas, i.e. SL modulo equivalence. You all remember set X modulo E, where E is an equivalence relation. Yeah, what is that? What are the elements of this? The equivalence classes with respect to that relation. Yeah, so this equipped with the following operations. The first one is of course 0. 0 is defined to be the class of the logical equivalence class of any contradiction. So, I chose this particular contradiction, yeah, for any P in L. I know P is always, yeah, for a non-empty, yeah, let us say non-empty. For empty propositional language, what are we going to do anyway? It is useless. So, let us assume our language is non-empty. 1 is the class of any tautology, okay. Then the third operation is I should define what is the meet of two classes. So, this is my first class and this is my second class. What should I define it to be?
S.
The class of S conjunction T. See, what we are writing, it still has to make sense. For S and T in SL. Now, please pay attention. This is a meet in the Boolean algebra and this is a conjunction in logic, and I promised you yesterday that we will see their connection. So, the meet in the Boolean algebra is obtained via this. Right now I am defining all these things, but they do not really make sense. Yeah, so we have to prove a result so that all these things make sense. All these definitions make sense. Okay, fourth point. How do I define negation? Sorry, complement. Complement of this. Any ideas? It is the class of negation, correct? Do I need to define disjunction? No, you already know what it is. Okay, so once again let me write this down. This is complement and this is negation. You can similarly define so for the above definition, to make sense, we need the following. First of all, yeah, I mean, let me call this a proposition again. First property is that this is an equivalence relation on SL. This is an equivalence relation. Can you see why? If S is equivalent to T and V is a valuation, then V of S is equal to V of T. And if T is equivalent to U, then V of T is equal to V of U. Therefore, V of S is equal to V of U. So, I do not need to write a proof of this. Second one, so this is a congruence relation. So, do you remember congruence from our earlier encounter with integers? Modulo n is a congruence relation, which means it is an equivalence relation which behaves well with respect to algebraic operations. So, what are the algebraic operations here? So, given S logically equivalent to S prime and T logically equivalent to T prime, we have negation S is logically equivalent to negation S prime. Why is it the case? Why is negation S logically equivalent to negation S prime? Because given a valuation V, V of negation S is true if and only if V of S is false, and V of S is false if and only if V of S prime is false, and V of S prime is false if and only if V of negation S prime is true. So you obtained the necessary connection that V of negation S prime is true if and only if V of negation S is true. All of you followed this? Okay. Then second property, that S conjunction T is logically equivalent to S prime conjunction T prime. So let us repeat the argument. V given a valuation V, V of S conjunction T is true if and only if V, S and T both are true for V, if and only if S prime and T prime are both true for V, and if and only if V of S prime conjunction T prime is equal to true. You can write these two lines. Okay. So this means it is a congruence relation, because observe here, when I am choosing two equivalence classes, I might choose some different element from that equivalence class, he might choose a different equivalence element from that equivalence class. If we choose different elements and we are defining their conjunction to be the class of the conjunction, then we still need to ensure that our values do not really clash with each other. I mean, whatever the result is, it is still in the same equivalence class. We don't want equality of the conjunctions. Yeah, if this is S and this is T, then we get S conjunction T. But if this is S prime and this is T prime, then we will get S prime conjunction T prime. We don't want the equivalence class to change. The actual formulas can change. Understood? So this is what we mean by this function is well defined on the set of equivalence classes. It means that it doesn't depend on what choices you make from those equivalence classes. And by the way, axiom of choice is not involved here, because we are only making two choices at a time. One from this equivalence class, one from this equivalence class. Two choices, you don't need axiom of choice. Or one choice, we don't need axiom of choice. Any questions here? Okay, so right now we know the Lindenbaum-Tarski algebra, which we will call BL. So this is in fact a Boolean algebra. Yeah, I mean maybe I should write that theorem. Because of this proposition, BL with meet, join, negation, complement, then 0 and 1. Well, in some cases we also write this as truth and this as false, yeah. Or maybe I should write it here also. Is a Boolean algebra. Okay, if you have a Boolean algebra, then first we need to look at some examples. So examples. First example, if L is equal to singleton P, then how many classes are there How many logical equivalence classes of L formulas are there? 4. Yeah, what 4 classes?
P, negation, P and Q and 4.
Right, so let me draw that picture. Yeah, the first one, the bottom one is of course the class of a contradiction. This is the contradiction. Then the top one is the class of a tautology. And what are the remaining 2 classes?
Class of P.
The class of P and
Class of negation.
the class of negation P. Okay. Second example. If L is equal to PQ, then size of BL is
8.
8. And how do you obtain that?
Negation.
See, how do you obtain the size of a finite Boolean algebra? You first count the number of atoms. Okay. If you count the number of atoms, then 2 to the atoms is. So, what are atoms? In this case, for a propositional language and this BL, Lindenbaum-Tarski algebra, what are atoms? Yes, loudly. Elements that are 0. S0L. S0L, see, okay, so that's actually a good thing to discuss. So, if I am given P and Q, then look at its truth table. It says TTFF and TFTF, that's how we start, right? Now, these columns contain 2 T's and 2 false. Well, I am using false. I shouldn't be using false. I have decided to use the other convention. But, okay, so tell me, if I have conjunction of P and negation P, what will be its column? The column is entirely false. Okay. Then, how many truths can there be in a column? At most 4, but at least 0. So, there are 5 different possibilities, and the number of truths will tell you the position in the Boolean algebra. Contradiction, which lies at the bottom, has no truths. The atoms must have exactly 1 true. So, can P be true? P be an atom? So, tell me something which can be an atom. P conjunction Q. P conjunction Q will have only 1 T, and then the rest of them will be false. So, this will be my atom, and there will be 4 in total. So, if the number of atoms is 4, then
16.
right. So, this is actually 2 to the power size of L. Because if I have 3 variables P, Q and R, what will be the atoms? P conjunction Q conjunction R, right? So, I am taking 2 conjunctions in that. And how many possibilities are there? What is another atom for this, for example?
Negation P,
Negation Q,
negation P, conjunction P.
Negation P, conjunction Q, yes. So basically for each variable we are making a choice. Either choose P or choose negation P, choose Q or choose negation Q, choose R or choose negation R. So for each variable there are two choices. So in particular, in total how many choices do we have? 2 to the power size of L. So those many atoms, we always have to use conjunction, conjunction, conjunction. That doesn't change. But 2 to the n, 2 to the size of L, many atoms. Correct? And then 2 to the power size of L, those many elements in the Boolean algebra. Now, are you wondering what is the order in this Boolean algebra? What is the order relation? So, this class is less equal this class if and only if this is in BL, if and only if what happens? The number of truths in S is now less equal the number of T's. That's not correct.
Merit of equivalent classes equals true.
Because I can have, see, this contains only negation P and yes, so this one is T and the rest of them are false. Now this column, this particular column contains exactly one true. Is this less equal the column for P? Just counting alone doesn't suffice.
To be in the same row.
Yes, exactly. Whenever you have a true value here, then you should also have the true value in the corresponding column for T. Correct? So that means if and only if S implies T is a tautology. See, recall what is the definition of truth for implication. Whenever S is true, then T is true. That's precisely what we wanted. Whenever you have a true in this column, then the corresponding truth should also hold for the column for T. Yeah, the definition for V of S implies T, like V of S implies T is true if either S is false, in which case we don't really care, but whenever S is true, then T should also be true. Right? So therefore, if and only if S implies T is a tautology. Okay. Now, in last few minutes, we are going to consider a similar situation for L countably infinite. Now tell me how many atoms should be there if L is countably infinite? Huh? 2 to the aleph naught? No. See, there will be first exercise tomorrow in the tutorial that even if your language is countably infinite, the number of formulas is still countably infinite. Formulas will not go beyond countable if your language is countably infinite. So therefore, you cannot use the same formula 2 to the aleph naught. No, that's too large.
No, they're bounded by finite sequences, so it has to be complete.
Yes, right. So you are giving a solution of that problem, that since every formula is a finite string of symbols, then SL should be countable. If SL is countable, then SL modulo equivalence relation is also countable. Yeah, you cannot make that set larger by taking quotient by an equivalence relation. But what's happening with atoms? Now there was something I wrote long time ago. Right? So if L is aleph naught, then BL is an atomless Boolean algebra. Please recall what is atomic Boolean algebra. Tell me, what is atomic?
It's an atom below here.
There is an atom below every non-zero element. Below every non-zero element. Okay. Now, if I can show that if I have a non-zero element, then there is something below it, something strictly below it and non-zero, then I will have proven that my algebra is atomless. See, because I start with an element, let me call that A0. If there is something below it and it is non-zero, A1, then A1 is non-zero, so for A1 there will exist A2 which is strictly below it and non-zero, and there will be an infinite chain, but this chain will never stop. So therefore I cannot have any atom. Okay, so given any S in SL, the solution to this atomlessness actually lies in the statement that Sriram made. Yeah, given any S in SL, since S is a finite string of symbols. String means word. Yeah, I mean, I'm just writing some symbols one after another. Since S is a finite string of symbols, it can contain only finitely many propositional variables. Okay, so given any S, it can only contain, I should say given any S in SL, S not a contradiction, because I need to choose something non-zero. Okay, I need to choose something non-zero, S not a contradiction. It contains only finitely many propositional variables. So choose a variable P in L that does not appear in S. I can do that. There is a variable that does not appear in S because L is countably infinite. So I can always choose a new variable. Then, okay, we have this. We have this inequality, strict inequality. The logical equivalence class of S has a strict non-zero lower bound. Namely, I just take the conjunction with P. Now, when S is not a contradiction, right? So, therefore, there exists a valuation V which makes S true. Correct? It is not a contradiction, which means there is a valuation. Let me quickly write this down. Yeah. So, since S is not a contradiction, there is a valuation V such that V of S is equal to true. If V of P is equal to true, then V of S conjunction P is also equal to true, and S conjunction P implies S is a tautology? Please verify that this is a tautology, and therefore bottom false is less than. Why it is strictly less than the class of S conjunction P? Why is it strictly less than? Because there is a valuation V which makes this true, and this is strictly less than the class of S. Why is that strictly less than and not logically equivalent?
Like previously we have shown.
No, it's not because of anything previous. See, there may exist, like right now we know valuation V, but if you change V, if you tweak V so that the value of P is false, then that valuation will still make S true. Yeah, let me write this down. If V dash is a valuation such that V of Q is equal to V dash of Q for all Q and L, Q not equal to P, and V of Q equal to V of P, V dash of P equal to false. Then now tell me what will be V prime of S? Yeah, because S does not contain P, so the values are not going to change. So then V prime of S is equal to true, but V prime of S conjunction P is false. Yeah, because P is not true, and therefore the class of S conjunction P is strictly smaller than the class of S. One last sentence. Yeah, I mean this argument worked because V of P was true. If V of P is false, then you instead use V prime to argue, and you swap the roles of V and V prime and the same argument will work. Correct? V was chosen because V of S is true. Yeah, you just swap the roles of V and V prime and it will work. So right now I have given you an example of an atomless Boolean algebra. In later part, when we study first order logic, we will see that this is the only countable atomless Boolean algebra up to isomorphism. There cannot exist anything else. Let's stop here.